समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Very good morning, everybody.
Good morning, sir.
Good morning.
Good morning, sir.
It's been a while since we took a together mode picture, so let's do that first. If you can all switch on your videos. Still only about half the class, I see. Hope those who have not applied ointment can join in. Okay, smile everybody. Just one more shot. Smile. Thank you. Previous class, as well as to some extent the one before that, basically the classes in the last week, we've been looking at certain questions related to composites. We started with why composites, why should we use composites, and then within the composite we looked at why certain components, in particular why the fiber, why the matrix. Having answered those questions to the extent of the scope of this course, we then moved on, and the next thing that we did was to answer the question where composites in the previous class. I was a little partial towards helicopters because that's been my passion or fascination for a long time. Right from my BTech onwards, my projects were all related to helicopters. In BTech, I built swash plate based mechanism to demonstrate the control systems for a helicopter. This was at IIT Madras, where we had developed a working model where there was a platform on which a student could sit and operate the control stick just like how the helicopter pilot would, and then see for himself or herself what is actually happening with the helicopter rotor blades. Though of course that was done with metallic structures, and then we could also see the coupling between the aerodynamics and the structures over there. So then, as far as my ME project was concerned, which was at IISc, it was basically to develop certain Floquet analysis for aeroelastic stability. So it was a computational project this time, looking at how the stability of a helicopter is governed by the various design parameters. So once again, a lot of structural inputs, but overall helicopter analysis as such. And then my PhD was sponsored by the Center for Excellence in Rotorcraft Technology at Georgia Tech, where we looked at composite rotor blades. So that was my first exposure to composites, both as a course as well as research. And then we looked at how bearingless and hingeless helicopter rotor blades, which are like cantilever beams as far as we structural engineers are concerned, how their designs can affect their behavior in terms of the various typical loads that are applied to it, and their nonlinear behavior in particular is what I explored. Apart from helicopter rotor blades, I looked at helicopter shafts, which are basically the transmission shafts going from the either the main rotor to the tail rotor, or the turbo shaft engine to the tail rotor to drive the tail rotor. How those thin-walled structures, circular shafts there would behave if made out of composites. So I have a little bit of partiality, you could say, for helicopters. A lot of projects that I've done after I've come back to India have been with HAL, the Rotary Wing R&D Center over there, RWRDC, towards developing certain systems for their helicopters. But nonetheless, having been in aerospace all through, there's been a lot of exposure that I've had through various companies like Boeing, Airbus, etc., with whom we have worked closely, as well as Indian entities like DRDO and ISRO, where we worked on problems other than helicopters as well. So you would see certain aspects of those research flavor coming in through some of these lectures as well. Though this is basically a very preliminary course in terms of giving an exposure to flight vehicle structures, I've always tried to make a case for introducing certain aspects of research so that you get a flavor of being in a master's course rather than purely an undergraduate like course, because your textbook is actually an undergraduate textbook, as I have said earlier. So, and this is primarily done because we want to expose the non-aerospace engineers to the aerospace. So now that we have answered the question on why and where composites, today we are getting into how composites, and which means that how do we analyze composites, how do we bring in composites into aerospace structure, like the examples that we saw at the end of last class. Because if you want to do it by a trial and error basis, which is what most of the initial adaptation was, then it involves a lot of money and, more importantly, cost, which is in terms of time towards development. But luckily, the modeling aspects have improved so tremendously that we are able to replicate a lot of things which happen in reality in the actual flying vehicles, as well as in lab-led tests on specimens using mathematical models. And whenever mathematical models are involved, certain assumptions are involved. But as long as you keep those assumptions realistic and to the extent possible mimicking reality, then you have an opportunity to use rigorous physics and state-of-the-art mathematics in order to arrive at models which are reliable. So it's that which will be the crux of this particular course, and so far whatever we have done is basically setting up that background in order to enter this. So you would see that we've minimalistically used equations so far in the course just to get on board all the other non-aerospace engineers so that they see where this applicability is there, just as we do. And then now that we are in that stage where we can have some kind of an understanding of where these things go, now we will delve into the mathematics aspects, especially from the next class. So today also we will be looking at certain assumptions, etc., which are related to how these structures in general and aerospace structures in particular, those made out of composites, can be analyzed, mathematically modeled and analyzed, so that we can then have much more confidence before we actually have to go for testing the optimized structures. So modeling structures is what we are getting into today. So in particular, we'll be looking at how to model composite structures for flight vehicles. So that would be the focus. And as I briefly mentioned in the last class, the composites have these complexities of anisotropy and non-homogeneity, which is what is making their analysis a little more difficult compared to that of metals. But metals have their own complexity when they enter into the plastic regime because they are ductile, and beyond the yield point, how they behave is something that we need to look at. But since composites include not only polymer matrix composites but metal matrix composites as well, where the metal behavior is taken into account and therefore plasticity as well. So we can think of the analysis of composites as a much more generic thing, where we are looking at specializing it for homogeneous being a special case of non-homogeneous, and anisotropy being the general case and isotropy being a special case of that. So we will see what all of these terms mean. Many of you are already aware of it, but we'll look at it in a little more rigorous fashion as we proceed with today's class, and probably to some extent the next class as well. So now we look at certain traditional modeling procedures, and this is what our entire analysis and design will be built upon throughout this course. Whereas in the analysis and design of composites course, as well as even more so in the nonlinear mechanics of composite structures course, we will go into non-traditional approaches to bring in higher reliability, by which we mean greater accuracy, but at the same time not sacrificing the computational efficiency too much. So that those kinds of approaches are beyond the scope of this particular course. So we will just stick to certain traditional approaches, very similar to what you see in your textbook, but certain times giving a little bit of flavor of the what is the current state of the art. So now in this traditional modeling procedure, you see that I've shown three pictures on the on your right hand side of the screen. So the one is basically at the lowest length scale that we need to go. There is quantum mechanics which goes even beyond that, which is of not much consequence over here. So, or molecular dynamics in between them. So those are aspects beyond the scope of this course. So the lowest length scale that we go to is of the order of a few microns, where we can actually see the fibers and the matrix. And even that is kind of an overkill for this particular course. So most of that we'll be touching upon in today's class, and we may not revisit even this length scale beyond today's class to a large extent. We might just very briefly mention this, but we will not go into the depths of the mathematics of this, because this is a subject area by itself. Some of your TAs, like for example Rajesh Nakka, are doing far more involved analysis of the micromechanics over here, Renuka Sahu too, and the other TA Vignesh is looking at even lower length scales in terms of molecular dynamics. But for this course, most of what we will do will be at the microns level, and we'll be mostly done with that in today's class itself. One of the things that large number of classes will be focused on is the next level, what we call as the mesomechanics at the lamina level, where a single layer is taken up in a laminate, and then most of the classes will be devoted to the laminate level, where a particular stacking sequence will be taken up, and we will look at how that can be analyzed based on information flowing from this way. So this traditional modeling process involves information transfer only from the lowest length scale to the middle length scale, and then to the largest length scale. Some of the students at NMCAD lab, which is where I work in the aerospace engineering department, look at the information transfer in the opposite direction as well to understand damage mechanics. So Renuka, for example, would look at a part of that, Rajesh too. So in terms of what kind of damages actually occur, and coming up with phenomenological models which are even more reliable than what you would see in this particular course. So mechanics for analysis and design is done at three sequential levels, as we saw in this figure, the one here, the one in between, and the third over here. So this is kind of a connection between the two, and so it becomes a very critical thing which we will spend quite some time on as we go forward in this course. So the most important thing is at the structural level, which can be thought of as a particular component. It could be a wing skin, it could be a spar, it could be a stringer, it could be a rib, whatever. But that is basically a laminate, in other words, a plate-like structure, which could sometimes also be a beam-like structure, like what is shown in this particular picture. So this is done usually for both metallic and composite structures. So many of the takeaways from what we do over here will be almost directly applicable to metallic structures as well, because we are all going to be restricting ourselves to within the elastic limit, and then the behavior is not very different. A specialized case of composites would be treated as metallic structures. So this is what we call as macro mechanics. macro meaning at a larger length scale, and therefore macro mechanics is at of the order of a meter or so, is what we are looking at, the structural geometries. And whatever is applicable there obviously is continuum mechanics. But even if we go to the micromechanics, we are still in the realm of continuum mechanics, but just that it's at a much lower length scale. So the micromechanics for metals is something that only material scientists typically do, where they look at the granular structure, the crystallinity, whether it is multiple crystals, polycrystal, or a single crystal, and if it is multiple crystals, how those grains are and how the grain boundaries are, how you can strengthen the grain boundaries to avoid cracks occurring at them, etc. Those are all things which typically material scientists look at. We do not. As structural engineers or aerospace engineers, most of that is given to us on a platter. And so for metallic structures, this is not at all visited by structural engineers. But for composite structures, at the micromechanics level, which means at the fiber matrix level, there's a lot of analysis which needs to be done, which is done by structural engineers. So this is something which is novel for composite structures as far as we structural engineers are concerned, and that is essential. But as I said, for this course, we would be visiting this only in today's lecture, not beyond that. But this meeting point between micromechanics and macromechanics is what is important at the lamina level, depending upon the particular angle at which it is. To start with, we will look at only 0 degrees, which is equivalent to looking at 90 degrees with just a very simple transformation. But we would start with 0 degrees, then we'll look at any arbitrary angle theta, which in this particular example of this figure is shown to be 45 degrees, but it could be any theta. How is the transformation done? Of the stresses, of the strains, and therefore the relationship between them is all that we will be looking at, and that will give us information to analyze any arbitrary sequence of theta 1, theta 2, theta 3, theta 4, etc. that are there. So in this particular case, you see it's an asymmetric laminate, neither symmetric nor antisymmetric. So because if you think of all of these 4 layers that are there in this laminate as of equal thickness, and then the mid plane is basically over here, and above the mid plane, immediately above you have plus 45, whereas immediately below you do not have a plus 45, you have a different angle, and therefore it is not symmetric. If it was plus 45, it would have been symmetric at that level, and if it was minus 45, then it would have been antisymmetric. But that has to be done for all the layers on the top and all the layers on the bottom. So this is a generic example of theta 1 being 0 degrees, theta 2 being 0 degrees, theta 3 plus 45, and theta 4 minus 45 degrees, a 4-layer sequence of laminae which become a laminate. Now, so we will go in steps. Today's class, we will look at micromechanics. Going forward, we'll look at mesomechanics at the lamina level, and then eventually we will look at the laminate analysis. So let's start with the micromechanical modeling as promised. The micromechanical modeling is the simplest model that you can have within micromechanical modeling, is that which is based on how you calculate, for example, the densities of mixture. Suppose you have a mixture of 2 materials, A and B. You know that the sum of the mass of material A and material B in a particular quantity of the mixture is equal to the total mass of the mixture. And you use that in order to calculate the average density of that mixture by multiplying the density of one material, let's say A, which we call as rho A, multiplied by the volume that occupies, which is VA, rho A into VA, plus rho B into VB, which would be nothing but the mass of A plus mass of B, is equal to the mass of the mixture. And using that, we come to a definition of what is known as a volume fraction. So you know by volumes how much of it is A and how much of it is B, and therefore the density, overall density of the mixture can, if we call that mixture as a composite, let's say rho C, is given by just rho of the fiber multiplied by the volume fraction of the fiber, which means the volumes of the fibers divided by the volume of the mixture as a whole, that is the composite as a whole. So suppose we call that a small VF, then you're basically looking at VF multiplied by rho F plus Vm multiplied by rho M. The sum should be equal to the density of the composite. So in other words, you're averaging out using a weighted average, which is the weightages being the volume fractions. So that's quite obvious from the fact that the total mass of the composite should be equal to the mass of the fiber plus the mass of the matrix, and therefore since the mass is equal to density times volume, we take advantage of that, divide by the total volume, and therefore now we are talking about not actual absolute volumes but volume fractions. What percentage of the volume is occupied by fiber, what percentage of the volume is occupied by the matrix, and that gives rise to that particular thing. On the other hand, we can do the similar thing for certain engineering properties of interest to the structural engineer. Of course, density is of interest too, but now we will talk about the Young's modulus along the longitudinal direction. So now you will see these abbreviations and subscripts, notations being used commonly. So you need to get used to this. Whenever we use a subscript L, we mean the longitudinal direction, which means the direction along the fibers. And when we use T, we mean the transverse direction, which is in a plane perpendicular to the fiber direction. It could be in this way or anywhere in between. That's basically a transverse direction that we talk about. And we will also use the subscript F to denote the fiber and the subscript M to denote the matrix. So when we say EM, for example, we are talking of the Young's modulus of the matrix. Here we are not using an L or a T just because we are considering the matrix to be isotropic, and which would be the case if, for example, you had a matrix which is, let's say, a polymer like epoxy or a metal like aluminium. In both cases, the matrix would be isotropic, so you don't need a direction dependence for the Young's modulus. On the other hand, the fiber, for example, carbon fiber, could be oriented in such a way that even if you take a single fiber, not only the composite, but just a fiber, its properties along the length could be different from its properties in the transverse direction. So it's important to specify that the Young's modulus of the fiber that you're looking at is along the longitudinal direction rather than the transverse direction. There could be certain fibers which are isotropic, which means they have the same tensile properties. And again, we need to mention whether it's tensile or compressive. So for this example, we are taking the tensile longitudinal Young's modulus, EL, of the composite that we want to determine. So unless otherwise mentioned, it's understood to be the composite. Sometimes we might call this as ELC to denote that it is of the composite, but where it is understood, we are saying that it is of the composite. So we are dropping that C, which is another subscript, just to say that it is property of the composite. Now these two small v's that you see, VF and VM, is the percentage or fraction rather of the volume occupied by the fiber and the volume occupied by the matrix. So for the simplest case where we are not considering any other additives and ignoring the porosity, which means the voids, VF plus VM should be equal to 1, because those are the only two materials that you are having in the composite, the fiber and the matrix, and therefore VF plus VM should be equal to 1. And the VF typical ranges are in the 40 to 60% range. There can be certain cases where you can go beyond that as well, and some cases where cost is concerned, you might go below that as well. But in many aerospace composites, you would see that it's in the range of 40 to 60%. That is the volume fraction of the fiber, and therefore the volume fraction of the matrix correspondingly would be 60 to 40% respectively. So that's basically what you need to remember as of now, because we are looking at only the simplest model, so to speak. So how do we actually get this? It's quite simple to see that. Are you able to see the whiteboard now?
Yes, sir. Yes, sir.
Okay. So now we consider, let's say, a layer of composites. So like this. And now let's say we have a few fibers in it. Okay, unlike the picture that I showed where I showed elliptical fibers, let's say we have some circular fibers in this. Rajesh, for example, in his research considers each of these fibers having different diameters, etc. as a parabolistic scatter, but we will consider, let's say, though I have drawn it differently in some cases, let's see. It's all the same fiber diameter. Okay, so now you have a layer something like this. Now what we do is, though the distribution can in general be random like this within the element, we are going to look at an equivalent homogenized structure. So we just take part of that, let us say an averaged homogenized part of that. So we take one particular element over here which consists of a single fiber and a matrix, and then we further simplify that like this, let's say, and then we think of a particular entire thickness being the fiber, and then let's call this region as the matrix M, and this region also as the matrix M, and this particular region as the fiber. Okay, now let's take a thickness or height of this as to be h, and then breadth we are always taking it as b. So now this fiber is running through the length of this, which we call, let's call the length as L, as we always do, and this overall breadth as B. Now this B, let's assume, is now broken up into two parts. One is the breadth of the fiber, that is, let's call that as BF, and then the sum of these two ends on either side of the matrix, which we will call as BM, assuming it's divided into equal portions on either side of BM by 2 and BM by 2, so that the total is BM, and so that the sum of these two is equal to the total breadth of that small element of the composite, which we will call as a representative volume element, or RVE for short. In other words, it is kind of representing the composite as a whole. So, but in what we want to go for is another equivalent homogenized structure. That is, instead of that, we are having something like this, where it is made out of a fictitious material, which we will now call as the composite, or C. Okay, and we would say that this composite is having the same geometry as this. In other words, it's having a height h, it is having a breadth b, and it is having a length L. Now this particular composite, unlike the actual representative volume element, is made out of a fictitious material which is going to have direction dependent properties, and we want to determine its properties in terms of the properties of the fiber and the matrix. And the simple example that we had is what we have over here, that is the longitudinal modulus of the Young's modulus of the composite in terms of the longitudinal modulus of the fiber and the Young's modulus of the matrix, and of course their volume fractions. So how do we go about getting this? As I said, this is the simplest model that we can go to. There can be many other more complicated and reliable models which can give you more accuracy, but for this particular course, this is good enough, and this is what we would stick to. So coming back to this, now suppose we apply a force along the length, which we shall call as a force F, big F, as opposed to the small f used for the fiber, and an equivalent opposite force in the other direction. Now it's easy to see that this force somewhere in the interior of this, if you look at a cross section over here, somewhere in the interior, far away from the boundaries, you're going to have St. Venant's principle coming into operation, and therefore we can think of the force being somewhat uniformly distributed within the fiber and uniformly distributed within the matrix, but the actual force carried by the fiber and the matrix could be different from each other. So let's call the force which is carried by the matrix to be Fm, and the force which is carried by the fiber to be Ff, and this sum of the force should be equal to the actual applied force, because there's no other material which is taking that, and this is because of the direction in which this is applied and the fiber being parallel to that particular direction. So this is very easy to see. Now this in turn is going to be equal to the stress in the matrix, which again we will assume to be constant for now, which is the case indeed as if you go into the interior, not close to the boundaries where the force is applied, and that force in the matrix will be equal to the constant stress in the matrix, which we call as sigma m. Again, of course, stress should be denoted by the actual subscripts of the plane on which it is acting and the actual direction in which it is acting. So in this case, it is actually sigma in the matrix in the L plane in the L direction, by which we mean, what is an L plane? The plane to which the longitudinal direction is perpendicular, because this is the direction of the fiber, and therefore this is the longitudinal direction, and also happens to be in this particular example the direction along which the force is applied, and therefore it's on a plane which is perpendicular to the L direction. For in some examples we could also call it one direction, so in that case it would be sigma 1 but here it is denoted as sigma LL, and because it is the stress in the matrix, we are showing it as sigma m. So that stress multiplied by the area on which it acts, which is equal to the breadth of that particular material, which is Bm, of course divided into two parts, half Bm here and half Bm over here, but the total is Bm multiplied by the thickness h. So that is the cross-sectional area that is exposed to the stress and therefore contributes to the force that the matrix takes, which is Fm. Very similarly, the force that is there in the fiber is now going to be given by the stress in the fiber, which we will call as sigma F, but now it is again in the direction L along the plane L. So once again, that is the stress that we are looking at. In some examples, you could call it as sigma 1 we'll call it as sigma LL, but in the fiber. And now what is the cross-sectional area of the fiber which is exposed to this stress? That is going to be given by the breadth of the fiber multiplied by the height, which is once again h. So breadth of the fiber we have denoted as BF and multiplied by h, which is the thickness or height of this representative volume element that we have taken. Now we come and say that the behavior of this equivalent homogenized quantity, let me write that. So equivalent homogenized material, which is a fictitious material, the equivalent homogenized material should behave the same way as this. In other words, if I apply a force F, the overall average deflection that is there in this should be observed in this as well. The idea of going from this to this is that we are having an equivalent homogenized material which will be easier to handle for a lot of things. So that is very critical in simplifying the problem. For a lot of things, we can then start dealing with the equivalent homogenized properties rather than the individual properties of the fiber and the matrix. So it leads to a lot of advantages, which is why this particular micromechanics results are very, very critical. So now this force that is there is going to act on this as well, the same force F on this fictitious element, and that force should now be equal to the stress in the composite, which we'll call as sigma C. Again, we are talking of the LL component, that is in a plane perpendicular to the L direction along the L direction, and multiplied by the cross section on which it acts. Now the entire cross section is available to it, that is B into H. So which is what we would put over here. Now we can divide this whole thing by BH. So if we do that, we get BMH by BH. So now we define the volume fractions of the fiber as the total volume occupied by the fiber divided by the total volume of the entire structure. The total volume of the entire structure is very easy to see to be HBL, because it's a simple cuboid structure that we have over here. The height of the fiber according to this RVE geometry that we have taken, very simplified, because we are just taking a rectangular cross section for the fiber. In reality, it is somewhat elliptical. Circular may be a reasonably good approximation for most cases, but this is a crude approximation but works for this simple model. So HBL is the total volume. The H remains the height of the fiber as well, but now we are having BF instead of B as the breadth of the fiber, and then the length is same for both the fiber and the matrix as well as the actual composite. So H and L cancel, so this just becomes, for the simple geometry that we have chosen for the representative volume element, it becomes BF by B. So that's what is the volume fraction of the fiber. Similarly, you can see that very easily the volume fraction of the matrix is going to be given by BM divided by B, right? So now if we divide this particular equation, let's call this as equation number 1. So if we divide equation 1 by BH, it's very easy to see that the H will get cancelled, and what you will have here is BM by B and BF by B, which is what we have seen as the volume fraction of the matrix and the volume fraction of the fiber. So substituting for that, so let me just remove that. Oops. And now replace BF by B by the volume fraction of the fiber, that is what we call as VF, and we replace, this is the matrix, so we call that as Vm, and this as the volume fraction of the fiber, and here the BH has got cancelled, so because we divided by BH, so this is what we have. Now, so this is very clear that this is the sum of the stress. Now we know that the stress is related to the strain, and another assumption follows. So mathematical modeling is always full of assumptions, because what you're doing is you're looking at a model instead of the reality. In going from the reality to the model, you'll involve a lot of assumptions. So whether those assumptions are valid or not is always a question. But in this case, for the simplest model, the assumption that is taken is that the extension of the fiber and the matrix is one and the same, because that's how this composite has to behave as a total, and therefore the amount by which the fiber extends and the amount by which the matrix extends is one and the same. So we will call, let me erase a few things over here. Okay, now so now we will come and write the stress sigma m as the strain in the matrix multiplied by the Young's modulus of the matrix. Now we have assumed that the matrix is isotropic, which would be the case if it's epoxy or even metal matrices like aluminum, etc. So it's a reasonably good enough approximation that you have over here. Similarly, for the fiber, we would take the stress in the fiber is equal to, now the Young's modulus of the fiber cannot be direction independent, it depends on the particular direction, so we will call it the longitudinal direction, and that is of the fiber, multiplied by the strain in the fiber. Now we are saying that the total deflection of the fiber, in other words, because we are applying a tensile load, it is extending its length from L to L plus delta L, and that delta L is common for the matrix, the fiber, as well as the composite. So we'll just call that as delta. So now this L has become, this L has changed to L plus delta L, and that delta L can now be related to the strains that you have in the fiber and the matrix as just delta L divided by L. Whether it is the fiber, whether it's the matrix, or the fictitious composite material which is equivalently homogenized, all of them have an extension delta L and original length of L, and so very easy to see that the strains, whether it is epsilon f, which is again of course in the LL direction, it's important to mention that the stresses as well as the strains that we are talking about are all in the LL direction. That's the component that we are interested in, and we see that all of these are equal to delta L by L. So you can go here and substitute for them, and you would see that the strains are going to get cancelled, because the same strain, whether it's in the matrix or the fiber or the composite, because of the fact that both the original length as well as the change in length are assumed to be the same for both these materials as well as the fictitious material. So then obviously that directly leads to the sigma MLL being replaced by the matrices Young's modulus, because the epsilon is going to get cancelled. This is going to be replaced by the fibers longitudinal Young's modulus, and this is going to be replaced by the composites longitudinal modulus, and therefore we end up with this particular equation that we had over here, that is ELF into VF plus EM into VM is equal to EL. In other words, the Young's modulus as far as the longitudinal direction is concerned is the weighted average of the same Young's modulus, that is along the longitudinal direction, again along in tension, but with a weightage, and that weightage, it's a weighted average, and the weightage involved is the volume fraction. Is this clear? It's a fairly straightforward thing, but if there are any doubts on this, I'd be happy to answer. Okay, so if there are no doubts, let's go further. Similarly, you can derive the Poisson's ratio. Again, you need to mention the direction. So whereas in the case of an isotropic material, you just denote by nu. And I also look at the difference between small v, which is used for volume fractions, and a nu, which is a Greek letter, which is used for the Poisson's ratio. For an isotropic material, you would have just one nu in any direction, but here you would make a difference between Poisson's ratio in different directions, just like you made the difference for the Young's modulus in different directions. In particular, we looked at the longitudinal direction earlier in tension. Now we are looking at Poisson's ratio in this fashion, where the first subscript would be the direction of the input and the second would be the direction of the output. So always remember, it's very simple and easy to remember this as a mnemonic. The input comes before the output. The output is a result and the input is a cause. So the cause always comes before the effect. So that is the thing that you have to remember. What does it mean, cause and effect here? Here it means that suppose I apply a longitudinal strain, I stretch something in the longitudinal direction. What is the effect in the transverse direction? So that is the effect that we are looking at. So the input is a strain epsilon L along the L direction, and of course there is also a strain, there is a stress and strain associated with that. That's a direct result. But the Poisson's effect is in an orthogonal direction. So it is basically involving a strain either in this direction or this direction, which is what is called as epsilon T and TT, because it's perpendicular to the T phase in the T direction. So that is basically what we are looking at. So it could be an epsilon 2,3 or epsilon 3,2 that we are looking at, and that basically is what is the output. So you are applying in the longitudinal direction the strain. You know how much strain you are applying in this, but now you are using a strain gauge to measure the strain in this direction, which would be a small fraction of this particular strain, and you would calculate that strain. So when you calculate that strain and take the ratio, that is what we define as the Poisson's ratio. And because the input was in the longitudinal direction and the output was in the transverse direction, we use the subscript in this particular order nu LT, which is very different from nu TL. So not only is it different in different directions, but when you interchange the input and the output, the value of the Poisson's ratio can change as well. So you can use a similar kind of procedure, slightly more involved, in order to show that nu LT is equal to nu LT of the fiber multiplied by the volume fraction of the fiber. Similarly, because the matrix is isotropic, we don't need to specify the subscripts LT over here, just like we didn't need to specify for the Young's modulus longitudinal direction. Here also we don't specify that, and so you have a Vm multiplying the volume fraction of the matrix multiplying the Poisson's ratio of the matrix, which is a constant throughout the matrix in whatever direction it might be. So this would be one of your homeworks, to derive this particular relationship by using a similar kind of an approach that we took to derive the fact that the longitudinal modulus of the composite is related to the longitudinal modulus of the fibers and that of the matrix through a weighted average, the weightage being the volume fractions of the fiber and matrix respectively. So same way you can show that the Poisson's ratio, if it is in the LT direction, is like this. Now for isotropic materials, you know that the Poisson's ratio has a particular range. Can anybody tell me what is the minimum and maximum values of the Poisson ratio?
It's 0 to 0.5.
Okay, good. Anybody else?
-1 to 0.5.
Okay. So the first answer is a subset of the second answer, but the second answer is more appropriate. Yeah?
Yes, sir. The second answer is correct.
Correct, yeah.
Yes.
So the reason for that is the limits on the bulk modulus and the shear modulus. If you actually see the shear modulus and bulk modulus, they can both be defined for an isotropic material in terms of the Young's modulus and the Poisson's ratio. E by 2 into 1 plus nu, for example, is the shear modulus. And the reason why that negative sign comes is because in the denominator you have a 1 plus nu, and as nu approaches -1, the shear modulus would become infinite. Similarly, you can show that the bulk modulus would approach infinity as the Poisson's ratio approaches plus half. There is plus 0.5, and therefore that is the upper limit that you have. On the other hand, this is something we will see a lot of these surprises when we go into composites. The Poisson's ratio for a composite need not have those limits. There can be some composites, depending upon, of course, the individual values of these, that can have values which are higher than 0.5 and lesser than -1 as well. Okay, so that is something that you should not be surprised by, because the definition for the or the derivation for the bulk modulus and the shear modulus will be different. So those expressions that you have for the bulk modulus of an isotropic material and the shear modulus of an isotropic material are no longer valid for an anisotropic material like a composite, and therefore the limits would be a little more complicated. They would not be the same limit for all materials. The limit itself would depend upon certain ratios of certain material properties, etc. In particular, the matrix Young's modulus will play a huge role. The Poisson's ratio of the matrix will play a huge role in the transverse direction. And in the longitudinal direction, it will be a combination of the properties of the fiber and the matrix which would play a huge role. Now, these examples are very easy to see for both the longitudinal Young's modulus as well as the longitudinal transverse Poisson's ratio, because it's a simple, straightforward series kind of a relationship. But a parallel kind of relationship, which many of you electrical engineers will also be familiar when you put resistors in parallel or inductors in series, etc. You have a difference between their behaviors. What is the total inductance or total resistance interchanges. Same way, if you go for the transverse direction, you would have quite different results. So this is what is the transverse Young's modulus of the composite in terms of the transverse Young's modulus of the fiber and the Young's modulus of the matrix, which is the same in all directions. And this in turn again depends on the volume fractions, but in a different way. A simpler way of writing this, of course, is 1 by ET is equal to VF by ETF plus VM by EM. So that when expressed, because we want to determine ET for the composite, that is the Young's modulus in the transverse direction for the composite in tension. we want to put ET on the left hand side and get everything in else which we know of the fibers properties, the matrices properties, and their volume fractions on the right hand side, known quantities, and we want to determine this unknown, so that's why we're pushing that to the right. Now determining that is somewhat similar to this, but just there's going to be an interchange in terms of what forces and displacement behavior is going to be, because now we are going to apply a force which is in this direction, which is the transverse direction, and now that force is not going to be divided between these two materials if you're going to take a representative volume element like this, because now they're like in series. So therefore that force acting on this is the same as the force which is acting on this, because if you take a cross section over here or anywhere for that matter, whether it's in the fiber or in the matrix, that force is going to be the same. So suppose again we call this force, just for a change, we call this as P, let's say, applied on either side. That same P is applied on both these sides here, and that same P is going to be acting on the fiber as well as the matrix. It's probably not appropriate to show it here because you have a part of the matrix over here. So let's say this P is actually applied on the representative volume element, because we are only interested in the equivalence between the representative volume element and the equivalent homogenized structure. So in the previous example, when we put the force F here, we saw that the force broke up into two parts, and the displacements were constant along the longitudinal direction. Now it's vice versa. In other words, the force is going to be constant whether it's in the fiber, matrix, or the composite, that is the fictitious material, and the displacement are going to get added up, because the amount by which in this direction, the horizontal direction, that the fiber is going to extend by and the matrix, two portions of it, is going to totally extend by, it should be equal to the amount by which the fictitious material, that representative volume element, is going to extend by. So therefore delta, which was a constant in the first example where we were trying to calculate EL by applying the force F, now when we are applying the force P, the transverse direction, that is along the direction perpendicular to the fiber, which of course is an entire plane, but we are looking at one particular example of that. So there the displacement is going to get added up. Delta is going to be equal to delta of the composite is going to now be equal to the delta in the fiber plus the delta in the matrix. And therefore we are once again going to use the same relationship between force and the stress, and between the stress and the strain, and between the strain and the displacement. But because of the fact that now displacements are getting summed up and the forces are equal, you end up with this kind of a relationship, a reciprocal kind of a relationship between, once again, the weighting factors or the weightages are in terms of the volume fractions of the fiber and the matrix, but just that the Young's modulus are there in the denominators, and therefore you have a little more complicated expression for this. So this is another of your homeworks, to use the simple rule of mixtures to derive this. You would find it in any textbook. You can just copy that. The whole purpose of this exercise is not to test your ability, but to understand the whole process of this very simple derivation, which you have done for many different examples, not only in mechanics but in electrical theory, etc. Same thing holds for the shear modulus as well, a reciprocal relationship. And once again, just like the Poisson's ratio, you need to express two subscripts. One is the input and the other is the output, both normal strains, and normal strain input in the longitudinal direction is resulting in a normal strain in the transverse direction. It's that ratio which we define as nu LT. On the other hand, GLT is in the LT plane. that is in a plane which involves the both the fiber as well as the matrix, that is the longitudinal direction of the fiber and the transverse direction. So if the fibers are along my fingers over here, that direction is the L direction. Any direction perpendicular to that is T, whether it is this or that. So this particular plane is the LT plane, in which you are basically having L and T directions, and therefore the shear in that direction, which is basically the in-plane shear for a plate, that modulus is going to be given by GLT, and in general it can be different from the G along other directions. One other important shear modulus that we need to be interested in is the GTT prime, because in this, if these are the fiber direction, then basically this particular plane that you have perpendicular to the fibers, it's the same whether you're having in this direction or this direction. Both are perpendicular to the fiber, because this entire plane is perpendicular to the fiber. So if we call this as the T direction, which is the transverse direction, this is also a transverse direction. Just to distinguish it, we will call it as T prime. So now we will be talking of a shear modulus G, which is having subscripts T prime, and that will be dominated by the matrix behavior, because the fiber would hardly contribute towards that. On the other hand, if you look at in this particular plane, that is the plane of the lamina itself, irrespective of whether it is the 0 degree or any other theta degree, all the way up to 90 or minus 90. So in this particular plane, the fiber plays a critical role as well, apart from the matrix. So in other words, GLT to some extent can be changed substantially by the fiber, but GTT cannot be changed too much by the fiber. You would see, if you actually derive the GTT prime, you would see that is almost entirely dependent on the matrix. Why is a little more complicated, because we are restricting ourselves to the rule of mixtures model, which works reasonably well for some of these, somewhat okay for this, and as we go for more complicated things like GTT prime, etc., it becomes or new TT prime, which is the Poisson's ratio, where both the input and the output are in the transverse direction, but of course in two perpendicular directions. That is, you apply a normal strain in this direction and measure using a strain gauge the strain in another transverse direction, which is orthogonal to direction in which you're applying the transverse strain, and you take the ratio of the output to the input strain, both normal. Then you get new TT prime. Your application direction being T and the output direction being T prime. So that example, those kinds of things would be using the simple rule of mixtures goes kind of awry, and because they are kind of matrix dominated, and you would typically end up with those very same assumptions that you make for these derivations no longer being valid, and or rather their validity is much lesser, and therefore the accuracy or reliability of those models are in question. So there are many other ways in which micromechanics can be done, which is again beyond the scope of this particular course. So if there are any questions related to this, I would be happy to answer. So your homework involves deriving the ET, nu LT and GLT using a simple rule of mixtures. So you feel free to make it an open book exam where you actually refer to something, and you can copy that, but do understand the whole process. That's very important to see what are the approximations made, why it is made, whether it is valid or not. If you can make certain comments related to that, you can get bonus points for the answer instead of just a simple derivation. So feel free to express yourself in terms of how valid or invalid you think these are, but don't go beyond the rule of mixtures. Even though you might be enthusiastic about it, let's not do that for this assignment. Stick to the rule of mixtures, but do comment on the validity of these approximations vis-a-vis the validity of the same assumptions when we did the derivation of EL, for example, and we quickly demonstrated that for ET without going into the details. So do go into the details in deriving these three expressions for nu LT, ET and GLT. As I said, GTT prime and nu TT prime, which are also very important quantities, matrix dominated, would not give very good results from using a rule of mixtures approach, and therefore it would be just waste of time looking at a rule of mixtures based derivation for them. So don't bother about them, just derive nu LT, ET and GLT. So any questions on this micromechanics?
Sir, can you just repeat a little bit about GTT prime?
Yeah.
Like how fiber isn't contributing much on GTT prime.
Very good. Yeah. So let's see what's actually happening over here. In GTT prime, you're basically looking at a plane which is perpendicular to the fiber direction. So if this is these are the fibers, you're looking at a plane which is perpendicular to that fiber direction, right? Now, in that plane, you see that if you apply a shear, what does it mean? So just think that the fibers are going between you and me. Now I'm only concentrating on this plane through which the fibers are coming out like this, and then on this plane I want to apply a shear stress. So that will be a tau T T prime, okay, and so that will have a complementary shear stress, which is now tau T prime T, and similarly again on this surface and this surface you would have all these stresses. Now imagine this. So this is basically a matrix through which the fibers are coming, and you're trying to shear these off. So now all you're trying to do is pull this apart to change that angle. So you have a 90-degree angle which is now going to change. The amount by which that right angle is going to change is a measure of your transverse shear strain, and it is these two quantities that the shear modulus GTT prime relates. That is, what is the shear stress that you're applying, which is tau capital T prime, divided by the change in the right angle that you have over here, which is gamma T T prime again. Once again, there is a difference between the engineering shear strain and the tensorial shear strain. I'm sure you're all aware of that by a factor of 2, taking that into account. But what is important in answering this question is to see that when this is happening, think of the fibers which are coming over here, and you're applying this shear stress, and this is changing the angle. It's very easy to see that since the fibers are going in this direction, they are not going to contribute much towards a shear strain which is happening. So whatever shear stress that is going to be applied over here is almost entirely going to be resisted and reacted to by the matrix, and therefore you see that
Sorry, I couldn't hear what you said.
That was Siri getting activated. Probably something that I mentioned was very similar to hey followed by Siri. Now what I'm talking about is, so you're applying a shear stress in this direction, measuring the change in the right angle. It's very easy to see, even though you have fiber reinforcement, because of the direction of the fiber reinforcement, it is this particular behavior in the transverse plane, which is perpendicular to the fiber direction, is going to be matrix dominated. So whether it is the Poisson's ratio nu TT prime or the GTT prime are going to be dominated by the matrix, because even though the fiber is present, it hardly plays a role. It will just move along with the matrix. As the matrix deforms, the fiber will just move. It does not offer sufficient resistance, and because it's not offering resistance, it's not contributing towards taking much of that stress, and therefore all the stress is taken by the fiber. So it's pretty much like in fact, one good approximation would be just to take the shear modulus in the TT direction as just that of the matrix. Similarly, the Poisson's ratio, and you would not be too far off. For a first cut preliminary analysis, many people do that. But of course, as I said, there are much more reliable micromechanics models way beyond the scope of this course. On the other hand, so let's contrast this with GLT, that is basically over here. Now, if you're talking of in this plane, I'm applying a shear stress. These are the fibers. My fingers are representing the fibers over here. Now I'm applying shear stress, which is on the T plane in the L direction. So therefore, I call this as tau TL. Why is this the T plane? Because it's the perpendicular direction is both perpendicular to the fiber as well as to this plane. So it's acting on the T plane in the L direction. So it is a shear stress, which we will denote as tau subscript TL. So same way on this, it's the L plane on which the stress is acting in the T direction, and therefore we will call it as the tau LT. So these are complementary and therefore numerically equal to each other under certain conditions, which we will come to a little later. But for most practical purposes in aerospace structures, we can always take that. So same way in all the other directions as well, other 4 directions of this, let's say, rectangular plate. Now, see what is happening. Now, because of this, I want to see what is the change in the right angle over here. That is, this right angle that you have is going to change by a certain amount, either increase or decrease depending upon the direction of these stresses, right? Now, that change in right angle is going to be determined by how the material reacts with stresses and strains, in particular, to the load that you're applying here in the form of a stress. So this stress is now trying to move this material to this particular direction, and now it's not just the matrix which resists it, because the fibers are in this direction. Trying to move a fiber like this through the matrix is going to be a little difficult. So therefore this particular shear modulus is slightly different in behavior to the shear modulus over here, where all the fibers are in the circular cross section, small, and they just move along with the fiber, do not offer much of a resistance. Whereas here, you're trying to move it perpendicular to the fiber length, and therefore what is trying to happen is the fiber also to some extent resists this particular motion, and therefore it would contribute to reacting to these stresses tau LT or tau TL, and therefore you would see that GLT has reasonable contribution from the fiber, whereas GTT prime does not have any major contribution from the fiber. Is that clear? Does it answer your question?
Thank you, sir. But I have a question. Like the compactness of the total composite, if we consider, we know that the presence of fiber is increasing the compactness. So the resistance to bear the shear will be also contributed by the fiber. Okay.
Yeah.
But in the case of TT prime, we are telling that the fiber is not contributing much. But would it be right? Can we tell that fiber won't react to that shear directly?
See, if it is not reacting, then it's also not contributing, because its way of contributing is through its reaction. So if it's just a silent partner in this whole partnership between the fiber and the matrix, it's not going to help. So that is basically what it is. So it is so that property where one of them is not contributing is dominated by the one which contributes. That's the whole idea. Yeah?
Thank you so much.
You're welcome. Anybody else? Any questions?
Hello, sir.
Yeah.
Sir, my question is that I just want to confirm that everything that we have derived till now, it is based on that we have assumed that everything is in linear domain and uniaxial load cases, right?
Yes, absolutely. Yeah.
Okay.
Yeah.
Thank you.
So in fact, very good that you brought this point up. In fact, in the next class, we will look at many of these assumptions, which are valid not only for the micromechanics or but also the macromechanics, and we will see when we are stretching that limit and when we have to let go of those assumptions, and what are the options available when those assumptions are not valid. What is the different way of doing it. We will have some kind of an exposure to those things. So the one point that you brought about is the linearity is very, very important over here. But see, that's why the principle of superposition is valid. As long as we have a linear model, the principle of superposition is valid. We are talking about the summing up the forces in one case, summing up the displacements in the other case. Many of these things are still valid. But the other things that we introduced in this particular example, we introduced the fact that the stress is proportional to the strain over here. That is a linearity. That can cause an issue in certain regimes. Again, when we introduce the strain in terms of the displacement, we called it as just delta divided by delta L divided by, that is the change in length divided by the original length. Again, when you have certain situations, and very common in aerospace engineering, we will visit that shortly. So that is not valid either. But this is still valid, that whatever force you're applying has to be taken by the two materials that are involved, and whatever displacement that is happening has to be encountered by those two materials, unless there is a fracture, unless there is a crack which is contributing to an additional amount of the displacement which is happening. We are talking of a healthy structure here, and in healthy structure these are fairly valid things. So the validity or invalidity rather does not come because of these expressions. It comes more because of what you're going to substitute into this. We substituted the force in terms of the stress, whether it's the true stress or whether it is the apparent stress, what kind of stress it is. All those things come into picture, and then when you are substituting the stress in terms of the strain, whether this equation is valid or not, and then when you are substituting the strain in terms of the change in length, is that valid or not? Those are the questions that will make some of these derivations invalid, not this itself per se. Fm plus Ff equal to F in one case, that is when the force is along the longitudinal direction, and in this case where it's along the transverse direction, the delta C is equal to delta F plus delta M. So these will be more or less valid. But of course, again, in terms of the geometry you're choosing for the representative volume element, it's highly questionable. Once you choose this geometry, yes, these two expressions are reasonably valid. But within those expressions, what you substitute is definitely not valid as you stretch the limits. Yeah?
Yeah, thank you, sir.
You're welcome.
Sir, can I ask one more
Yeah,
question?
please go ahead. Yeah.
I just had one doubt. This whenever we talk about the shear stresses, or basically the shear strain, actually, we talk about the angular change in angle between two perpendicular lines.
Correct.
Right?
Correct.
How this 90 degree changes to 90 plus theta or 90 minus theta.
Correct.
That theta is actually the strain.
Right.
So why cannot we talk about two other lines which are not perpendicular to each other in the material? That can also happen, but like say we don't have a rectangular cross section but some skewed cross section kind of thing. There we don't have, the edges are not perpendicular, right? So why don't we talk about those things? Excellent
point. See, there are two answers to this particular question, or the two parts to it. First of all, recognize that whether it's the stress, strain, or the moduli, all of these are quantities at a point. For what we are showing are infinitesimal elements that we are showing over here. So the shape of that element can always be taken as a cuboidal structure, even if the overall structure is not cuboidal and is having edges which are not perpendicular to each other. It could be a trapezoidal structure, but we are interested in what's happening at a particular point or a particular cross section. We can take a rectangular situation over there. The other more generic point is that it's not at all restrictive to orthogonal coordinate system. Just that we have got used to this Cartesian coordinate system of x1, x2, x3 with unit vectors b1, b2, b3 perpendicular to them. But you can, for all practical purposes, use a curvilinear coordinate system, and which might be very convenient in certain cases where these are not orthogonal to each other. Not only are they not orthogonal to each other, they need not even be straight lines. So these can be three curves: x1 coordinate curve, x2 coordinate curve, and x3 coordinate curve. As long as they are not parallel to each other, any three which are not parallel to each other can be used to combine, because we are talking about a three-dimensional space. And in a three-dimensional space, as long as if it's straight lines, we're talking of non-collinear. So in other words, two lines should not be parallel to each other. But now when you're talking of coordinate curves, you have to talk about those which are not identical to each other or parallel to each other once again, but it can be in any direction. So what we're talking about is a right angle changing its angle by theta, and therefore the shear strain proportional to that, depending upon whether it is engineering or tensorial shear strain, but it's directly related to that change in 90 degrees. But now what if you had an infinitesimal element which is not 90 degrees, you can always still find out the change in angle over there and relate it to this. This is just a baseline that we are having in terms of 90 degree for convenience, but need not always be. But you have to be careful that once you define it in a particular way, you take that definition into account throughout all your derivations, and you'd still not go wrong in terms of the overall behavior prediction in terms of for a certain load that I apply on this structure, how it's going to deform, etc. You're just going to make your life more complicated in terms of the derivation. But yes, there could be certain geometries for which what you're saying might actually help you to simplify the derivation. So there's absolutely nothing wrong in that. As long as these two are not collinear, the change in angle is what we are interested in, and we can always map it to a right angle changing its angle by a certain amount, and those two will be related to them each other in some extent. So you'll have to derive that geometric equation. See, this is basically strain versus displacement or rotation. So it's entirely geometry. The material is playing no part here, whether it's a composite, whether it's a metal, it doesn't matter. It's pure geometry that we are talking about in a 3D Euclidean space that we are now dealing with. And there we are talking about a change in geometry of a 90 degree plane, two planes which are at 90 degrees to each other, as opposed to two planes which are not necessarily orthogonal to each other, and how to relate these two rotations that are happening. And again, rotation can be of two parts. One is the rigid body like rotations that are having, and the shear rotations. So you need to separate these out, and it's much easier to do that when you're dealing with orthogonal coordinate systems like Cartesian rather than with an angular coordinate system or a curvilinear coordinate system. Is that fine?
Yeah, thanks a lot, sir. Means those things are there, and we do use those things in certain cases.
Absolutely, but very, very rare cases. Yes, it depends upon the particular geometries which are involved. So you can do that. For most practical purposes, your Cartesian coordinate geometry is more than sufficient.
Okay, thank you, sir. Thank you.
Because as I said, it's not the overall structure's geometry that is important. Because at a point we are taking an infinitesimal element, and that infinitesimal element can always be chosen to be cuboidal irrespective of the overall shape of the structure. Yeah, anybody else? Any questions? Okay, so I think with that probably we will stop today's class, because I'm going into a new topic after that. So let's not confuse there. So this is your homework for today, to derive nu LT, ET and GLT. Make it very clear step by step without missing any steps, and at each step what are the assumptions involved, and whether you think that assumption is really valid or not. So these are the things that I want you to give thought towards, rather than actually trying to derive it yourself, because I know at least some of you would anyway go to books. So that's why I'm making this an open book exam where you actually refer to books, because you have that privilege any time. So you refer to the books, but try to ensure that you give a thought to it. Each step, what is happening, what are the assumptions involved, how valid are those assumptions. So try to comment on those things, which is what is much more important in any derivation for that matter. Okay, so thank you very much, and see you on Thursday.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome. See you.
Thank you, sir.
Most welcome.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा मृत्यवे स्वाहा